In 1837, north of New York City, a crew of immigrant laborers stood beside the Croton River and began building something most people would never see. Not a bridge, not a church, not a railroad station, not a monument with statues and speeches around it. They were building a buried river. A 41-mile line of masonry, tunnels, embankments, culverts, reservoirs, and stone arches that would carry clean water from rural Westchester County to Manhattan by gravity alone. The city at the other end was thirsty, and sick, and burning. New York had grown faster than its water supply. Wells were contaminated, ponds had become filthy. The surrounding rivers were brackish. Fires could rage because there was not enough reliable water to fight them. Disease moved through neighborhoods where people drank from sources poisoned by waste, animals, industry, and crowding. In 1832, cholera killed thousands of New Yorkers. In 1835, a major fire destroyed hundreds of buildings in lower Manhattan. The city could keep growing upward and outward only if it solved a basic physical problem. Where does a crowded island get enough clean water? The answer was the Croton River. But the Croton River was more than 40 miles away. Between the river and Manhattan were hills, valleys, farms, streams, rock, mud, property lines, politics, and the limits of early American engineering. There were no tunnel boring machines, no hydraulic excavators, no diesel trucks, no concrete pumps, no laser levels, no modern surveying instruments, no giant trenching machines, no powered rock drills. The workers had picks, shovels, black powder, stone, brick, hydraulic cement, horses, carts, wheelbarrows, derricks, levels, plumb lines, and the command of gravity. They had to build a water system so precise that a river could travel 41 miles and still arrive with enough force to change New York. This is the story of the Old Croton Aqueduct, the buried machine that carried clean water to New York before modern construction equipment existed, and the workers who cut, dug, hauled, blasted, bricked, and buried it into the landscape. To understand why New York needed the aqueduct, start with the city before Croton water arrived. For generations, Manhattan relied on local water, wells, springs, cisterns, the collect pond in lower Manhattan. At first, these sources were enough for a smaller town, but New York did not stay small. Population rose. Buildings crowded together, animals filled streets. Workshops, tanneries, slaughterhouses, privies, stables, and households all produced waste. The same shallow ground that supplied water also absorbed filth. The city was surrounded by water, but much of it could not be drunk. The Hudson and East Rivers were tidal and salty. Local ponds and wells became unreliable or dangerous. The island was wet but thirsty. That is a hard thing for modern people to feel. Today, turning a faucet feels like a small act. In early New York, water was work. People hauled it, bought it, stored it, carried it in buckets, depended on public pumps, relied on private wells, and when those sources failed, went without enough. Bad water was not just inconvenient, it was deadly. Cholera did not need a dramatic battlefield. It needed contaminated water and crowded people. Yellow fever and other diseases also haunted the city. Doctors and officials did not yet understand germs the way later science would. But New Yorkers understood that foul water and sickness traveled together. They also understood fire. Most of the city was built with combustible materials. Dense blocks burned quickly. Without abundant water under pressure, firefighting could become desperate. The 1776 fire had destroyed a quarter of the city's buildings. The 1835 fire burned through lower Manhattan and showed, again, that the city could not protect itself with its existing water supply. So New York's water problem was not one problem. It was three: drinking, sanitation, fire. A city can tolerate inconvenience for a long time. It cannot tolerate a water system that poisons residents and fails when buildings burn. By the late 1820s and 1830s, the political will finally caught up with the physical need. The city looked beyond Manhattan for a new source. The Croton River, in what is now Westchester County, offered something local wells could not: elevation, clean water, volume, distance from the worst pollution of the city. The river sat high enough above Manhattan that gravity could do much of the work. That was the key. Before modern pumps could move water cheaply at enormous scale, elevation was power. If the source was high enough and the route was graded correctly, water could flow without an engine. That sounds easy until you try to build it. Water will flow downhill, but it will not forgive bad grade. Too steep, and the current can damage the conduit. Too flat, and the water slows, settles, and fails to deliver what the city needs. Too low at one point, and the line may lose pressure. Too high at another, and the water cannot climb. The whole 41-mile system had to descend gently, deliberately, and continuously toward New York. That was the hidden precision of the aqueduct. It was not enough to dig a ditch. The workers had to create a controlled artificial river with the correct slope through real terrain. Hills did not care about the calculation. Valleys did not care about the plan. Streams crossed the route. Roads crossed the route. Property owners resisted. Rock interrupted. Wet ground collapsed. The line had to keep going. This is where the old method comes in. The first chief engineer, Major David B. Douglas, planned the route in hydraulic principles but was later replaced by John B. Jervis, who led the final design and construction. Jervis was already known for canal and railroad engineering. He understood that the Croton project was not just one structure, it was a chain. A dam to hold water, a reservoir to store it, a covered masonry conduit to carry it, tunnels where hills stood in the way, embankments where valleys had to be crossed, culverts and waste weirs to manage excess water, ventilators to allow access and air, a bridge over the Harlem River, a receiving reservoir in Upper Manhattan, a distributing reservoir at Murray Hill. Break one link, and the city did not get water. That is why the Croton Aqueduct belongs in built before machines. The object was not a single dramatic tower. It was a system, and systems are often harder to remember than monuments.
The Old Croton Dam was built about 6 miles above the junction of the Croton and Hudson Rivers. It created a lake several miles long, storing hundreds of millions of gallons of water. That was the source. But the source alone did nothing for New York. The water had to travel. The aqueduct itself was built of stone, brick, and hydraulic cement. Its covered conduit was shaped like a horseshoe, large enough for a man to enter for inspection and repair. Some descriptions give its cross-section as roughly 7 feet wide and 8 feet high. That means the water tunnel was not a pipe in the modern household sense. It was a walkable masonry passage, a hidden canal with a roof. Workers had to excavate for it, build it, seal it, cover it, and protect it over mile after mile. Imagine the daily work. A cut opened in the ground. Laborers dug with picks and shovels. Rock had to be drilled and blasted with black powder. Stone was quarried, shaped, and hauled. Bricks were laid. Cement was mixed. Masons formed the curved interior. Spoil was loaded into carts. Horses pulled loads where they could. Men pushed wheelbarrows where animals could not. Surveyors checked grade again and again because the entire project depended on slope. Then the completed section was covered, and the crew moved on. The aqueduct disappeared almost as soon as it was built. That is the strange thing about water infrastructure. The work is enormous, but the final success is quiet. The city does not need to see the conduit. It needs a drink from it. Nearly 4,000 immigrants worked on the Croton system. Many were Irish laborers, part of the same hard 19th century workforce that built canals, railroads, roads, sewers, docks, and foundations across the country. Their work was low-paid, dangerous, and physically relentless. There were no excavators to make the trench, no dump trucks to carry spoil away, no power drills to eat rock, no modern trench boxes to protect men from collapsing walls, no modern hard hats, no safety agency watching over blasting. The project required the kind of labor that changes bodies. Hands blistered, backs bent, shoulders carried, lungs took in dust, feet stood in mud, arms absorbed hammer shock. Men worked through heat, rain, cold, and the constant pressure of a public project that had to succeed. They were not just building for a private mill or a local road. They were building survival capacity for America's largest city. That fact made the work important. It did not make the work gentle. The aqueduct route crossed a landscape that was rural compared with Manhattan. Farms, villages, woodlets, streams, roads, and hills stood where the line needed to pass. New York City used eminent domain to take land for the system. For the city, this was progress. For rural property owners, it could mean losing land, moving, or seeing a distant city's needs imposed on their countryside. That is another hidden cost of infrastructure. Water for one place often begins as disruption in another. The Croton system did not simply bring pure water from nowhere. It took water from a watershed. It dammed a river. It flooded land. It cut across property. It changed the relationship between New York City and the rural communities north of it. The city's thirst reached into the countryside and rearranged it. That pattern would repeat later on a much larger scale with the Catskill and Delaware water systems. But Croton was the beginning. The first great step in New York learning to reach far beyond its borders for water. At the construction site, the technical problem remained physical and immediate. How do you keep the grade? How do you cross a valley? How do you pass through a hill? How do you keep water inside masonry for 41 miles? How do you keep the line from freezing, leaking, cracking, clogging, or settling? How do you inspect something meant to be buried? Each question required a structure. Where the land fell away, workers built embankments or arch structures. Where streams crossed, they built culverts. Where the aqueduct needed to discharge extra water, they built waste weirs. Where the route met the Harlem River, they built the High Bridge. The High Bridge became the most visible part of the Old Croton Aqueduct. It carried the water line across the Harlem River into Manhattan. A buried conduit could hide under fields and roads for miles, but a river crossing had to show itself. Stone arches rose above the water, carrying the aqueduct across the gap. To modernize, the High Bridge looks like architecture. To the Croton system, it was a necessity. Gravity had to continue. The water could not simply drop into the Harlem River and climb out again. The line had to cross while holding its elevation. That is why aqueduct bridges exist. They're bridges for water. The public sees arches. The engineer sees grade. The worker sees stone that has to be lifted, cut, set, and made to hold. Building the High Bridge required a different kind of labor from digging the conduit. Stone piers, archwork, false work, masonry, lifting, alignment, working above water. Every arch had a transfer load. Every pier had a stand. The bridge had to carry not crowds or wagons, but the pressure of the city's future water. That is an almost poetic idea, but it was not built poetically. It was built with stone, timber, scaffolding, ropes, derricks, hoisting gear, and men. While the aqueduct advanced south, Manhattan waited. The city was preparing reservoirs to receive the water. The receiving reservoir was built in what is now Central Park, near the site of today's Great Lawn. From there, water traveled farther south to the Murray Hill Distributing Reservoir at 5th Avenue and 42nd Street, where the New York Public Library stands today. That reservoir was not a small tank. It was a massive stone structure, a civic object in its own right. New Yorkers could walk around it and see, in stone, that the city had changed. The water system was not hidden completely. It surfaced in reservoirs, gatehouses, bridges, and fountains. But the real line, the 41-mile machine, remained mostly buried. The project took years. Construction began in 1837. On July 4th, 1842, Croton water reached the city. That date mattered. Independence Day, a public celebration. Water flowed into Manhattan not as a private convenience, but as a civic triumph. There were fountain displays. There was a parade. People understood that something enormous had happened. New York had not merely found more water. It had built a new relationship with distance. The city could now drink from a river far beyond its edge. That is what made the aqueduct revolutionary. It extended the city through infrastructure. Manhattan was still an island, but its water source now reached into Westchester. Its daily life depended on a buried route through other landscapes. That is how modern cities grow. They stretch invisibly. Their food comes from elsewhere. Their fuel comes from elsewhere. Their water comes from elsewhere. Their waste goes elsewhere. The Croton Aqueduct was one of New York's first great invisible extensions, and it was built before modern machines could make such work routine. The first rush of Croton water changed everyday life. Firefighting improved because the city finally had a large, reliable supply. Public fountains could run. Street cleaning became more possible. Bathing and household use changed. The city's confidence grew. Clean water helped New York become a larger and more livable urban center. But the success created another problem. Once people had abundant water, they used more of it. Flush toilets, sewers, bathhouses, industry, street cleaning, and population growth all increase demand. Infrastructure often does that. It solves scarcity, then teaches people to live as if scarcity is gone. The Croton system had been designed for a growing city, but New York outgrew it quickly. By the late 19th century, the city needed the new Croton Aqueduct, larger and deeper, and eventually the Catskill and Delaware systems. That does not make the Old Croton Aqueduct a failure. It means it succeeded so well that it helped create the next scale of need. This is one of the deepest patterns in American infrastructure. The solution becomes the foundation of a bigger problem. Build a canal, and trade grows. Trade demands railroads. Build a water system, and the city grows. The larger city demands more water. Build a bridge, and traffic grows. The increased traffic demands more crossings. Progress does not end demand. It changes the size of it. For the workers, none of that future was certain. The man laying brick in the aqueduct conduit was not thinking about 20th century reservoirs. He was thinking about the next course. The man hauling stone was thinking about the load. The man drilling rock was thinking about the hole. The man standing in a trench was thinking about the wall above him. The worker's world was immediate. That immediacy is easy to lose when we tell the story from the city backward. From New York, the Croton Aqueduct looks like a visionary public work. From the trench, it looked like labor. Mud, stone, brick, powder, horses, injuries, long days, measure grade, more digging. That is the BBM angle. Not simply that New York got water, but that water had to be physically persuaded to travel. Every foot of elevation mattered. Every joint in the masonry mattered. Every tunnel had to line up. Every bridge had to carry the conduit. Every reservoir had a hold. Every worker was part of a system whose final product was not a building, but flow. Flow is hard to film. It is harder to remember. A skyscraper stands in front of you. A bridge frames a skyline. A dam rises like a wall. An aqueduct mostly hides. But hidden does not mean small. The Old Croton Aqueduct carried tens of millions of gallons of water a day. Some descriptions put the early daily delivery at around 45 million gallons, while later capacity figures are higher. The exact number varied with time and operation, but the practical result was unmistakable. New York finally had a water supply large enough to change the city. The aqueduct turned gravity into a public utility. That is the strange machine at the center of this story. Gravity, stone, brick, cement, distance, slope. The machine had no engine because the landscape itself was the engine. The Croton River sat high. Manhattan sat lower. The aqueduct connected the two through a controlled descent. Water moved because the builders respected that descent. If they had been careless, the system would have failed. That is why surveying was as important as digging. Old surveyors did not have modern electronic tools. They worked with levels, rods, chains, sight lines, notebooks, calculations, and patient repetition. The aqueduct's grade was slight enough that small errors mattered. A careless rise in the line could slow water. A bad settlement could create weakness. A poorly made joint could leak. A bad foundation could crack the conduit. The beauty of a system was not speed. It was continuity. 41 miles of continuity. That continuity was made by thousands of small correct acts. Dig to the right depth. Set the stone. Lay the brick. Shape the arch. Mix the cement. Check the grade. Backfill carefully. Move forward. Do it again. That repetition built the buried river. The Old Croton Aqueduct also changed what New Yorkers expected from government. Earlier private schemes had failed to solve the water problem adequately. The Manhattan Company, created in 1799 to supply water, became more famous for the bank it created than for delivering clean water well. By the 1830s, the city needed public action on a scale private wells and wooden pipes could not provide. The Croton Project showed that a city could tax, borrow, condemn land, hire engineers, organize labor, and build a regional system for public health and safety. That was not only engineering. It was state capacity. It was the city learning to act like a modern city. But the state did not swing the pick. The workers did. The public authority created the project. The laborers created the aqueduct. Both facts are true. The uncomfortable part is that the benefits and burdens were not evenly shared. Manhattan gained clean water. Rural landowners lost land. Immigrant workers took the hardest physical risks. City residents celebrated fountains and parades. Men in cuts and tunnels went back to work or moved on to the next hard job. That imbalance does not erase the achievement. It makes the achievement more honest. Infrastructure always has a geography of benefit and burden. The Croton Aqueduct's benefit flowed south. Some of its burden remained north. That is worth remembering because later New York water projects would repeat the pattern on a larger scale, taking water from farther watersheds and reshaping entire communities for the city's needs. The old aqueduct was the first chapter in that story. The human story also includes the people who maintained it after construction. An aqueduct is not finished just because water flows through it once. It has to be watched. Leaks have to be found. Weirs have to work. Ventilators and access points have to be kept usable. Embankments have to be inspected. Reservoirs have to be managed. Water has to be measured. Keepers and superintendents became part of the system. They lived along the route, walked sections, reported problems, and kept the invisible machine operating. Maintenance is less dramatic than construction, but it is just as essential. A neglected aqueduct becomes a ruin. A maintained aqueduct becomes a city service. That service continued for more than a century. The Old Croton Aqueduct remained part of New York's water supply until 1955. By then, the city had long outgrown it. Newer, larger systems had taken over. But the old line had done its work. It had carried water through the age of horse carts, gaslight, Civil War, elevated trains, early skyscrapers, automobiles, subways, and modern New York. Think about that span. A system begun with picks, shovels, brick, stone, and immigrant labor remained useful deep into the 20th century. That is not primitive. That is durable. Today, much of the Old Croton Aqueduct route survives as a trail and historic corridor. People walk above it, jog above it, push strollers above it, ride bikes near it, pass old ventilators, weirs, gatehouses, and traces of masonry without always knowing what lies underneath. The route has become quiet, green, local, almost peaceful. That peacefulness can make the original work harder to imagine. Where there is now a path, there was once excavation. Where there is now shade, there were cuts, embankments, and construction camps. Where people now walk for recreation, men once worked to make a city survivable. The High Bridge, restored for pedestrians, is one of the best places to feel the old system. Walk across it, and you are walking on a bridge that once carried water into Manhattan. It is easy to look at the arches and think of beauty. But the beauty had a job. The arches held a grade. They carried flow. They kept the artificial river high enough to continue into the city. That is the kind of infrastructure BBM exists to notice. Not only the landmark as scenery. The landmark as a solved physical problem. New York needed water. The water was 41 miles away. Gravity could bring it, but only if workers built a path precise enough for gravity to follow. That is the core of the story. The physical problem. A crowded island lacked clean, reliable water. The old method. Hand-dug trenching, masonry conduit, tunnels, embankments, reservoirs, and aqueduct bridges. The strange machine. A buried, gravity-fed river. The human cost. Immigrant labor, dangerous excavation, land condemnation, years of hard work, and the public health disasters that made the project urgent. The legacy. New York's first successful public water supply system, a city transformed by clean water, and a historic route still visible under parks, paths, and bridges. What replaced it? Bigger water systems. The new Croton Aqueduct, the Catskill system, the Delaware system, deeper tunnels, larger reservoirs, modern treatment, modern monitoring, millions more people served by a water network that stretches over a vast watershed. But the logic remains recognizable. Find clean water, store it, protect it, move it by gravity when possible, bring it to the city. The modern system is larger and more complex, but the Old Croton Aqueduct taught New York the pattern. It showed the city that survival could depend on infrastructure far beyond the city line. It showed that water could be engineered as a regional system. It showed that public health, fire protection, growth, and urban confidence all begin with something as basic as water arriving when needed. And it showed that before modern machines, building that confidence meant digging a 41-mile path by hand and masonry. The next time someone walks past the New York Public Library at 5th Avenue and 42nd Street, they may not think of water. But that site once held the Murray Hill Distributing Reservoir, a massive stone symbol of Croton water, a reservoir where New Yorkers could see the new system made solid. The library came later. The water came first. The same is true in Central Park, where the receiving reservoir once occupied ground now associated with the Great Lawn. The modern city has overwritten parts of the water system. That is what cities do. They build on their own solutions. But underneath the changed landscape is the memory of a moment when New York had to admit that wells and local ponds were not enough. It had to reach north. It had to build big. It had to trust engineers. It had to employ thousands. It had to take land. It had to cut a hidden line through the country. It had to become a city that could feed itself water. That is not a small transformation. The Croton Aqueduct did for water what canals did for freight and railroads did for movement. It connected need to source. It collapsed distance. It made the impossible routine. That is what the best old infrastructure did. It did not make life dramatic every day. It made life less desperate. A mother could draw water. A firefighter could fight. A street could be washed. A factory could operate. A city could grow. Those daily outcomes were the point. The aqueduct was not built so people would admire an aqueduct. It was built so people would stop thinking about water as constant fear. Successful infrastructure becomes boring. That is its victory. But boring systems often have dramatic origins. The Old Croton Aqueduct began with epidemics, fire, political failure, contaminated wells, and a city on the edge of its own limits. It became a buried route through hills and valleys. It became a bridge over the Harlem River. It became reservoirs in Manhattan. It became fountains on Celebration Day. Then it became habit. That is the full journey. Crisis, labor, engineering, celebration, habit, and finally, memory. Built before machines, lives in that memory. It asks what had to happen before the faucet felt normal. Before New York could take clean water for granted. Before gravity became part of the city's daily life. Before modern equipment made large water projects easier to imagine. Someone had to stand in a trench north of the city and make the line true. Someone had to cut stone. Someone had to lay brick. Someone had to blast rock. Someone had to haul spoil. Someone had to build the dam. Someone had to carry the conduit across the Harlem River. Someone had to finish mile after mile of work that would mostly disappear under earth. That is the worker's paradox. The better the work, the less visible it becomes. The aqueduct did not need to be seen. It needed to flow. And for more than a century, it did. If this story made you see New York's water differently, subscribe to Built Before Machines. This channel exists to remember the workers, tools, strange machines, and dangerous methods that built America before modern construction equipment took over. The algorithm remembers skylines. It remembers bridges. It remembers towers. It remembers what rises above the street. But it forgets the buried river under the path. It forgets the immigrant laborers who built 41 miles of masonry so a city could drink. Before New York could become the modern city people know, it needed water from beyond itself. And before that water could arrive, workers had to build a river underground.